In this video, we're going to prove the following theoretical result. We assume that an is strictly bigger than 0, and we also assume that the series of the a case k going, or an going from 0 to infinity or from some other number to infinity is convergent. We want to prove that the series defined by the natural log of 1 plus an is also convergent. This is a theoretical proof exercise, and before we start, we can give some hints. We want to use the comparison test to prove this result. We can also use this fact here that we have to prove is that ln of 1 plus x is less than x. So that's what we wanna do. So we wanna prove that the natural log of 1 plus x is less than x. Okay. So in fact, we can prove this one using graphing. Okay. So we know the natural log of x is this one. Okay. So the natural log of 1 plus x is just this one shifted 1 unit to the left. So it's going to be parallel to this one. So this is the natural log of 1 plus x. I'm not drawing them nicely, but you get the idea. So x is this one here. X is on top, okay? So x is bigger. So it should be a line. Y is x. But you see what we want to say. It's on top of it, that means it's bigger. Okay? But we are only concerned about this one here, when x is bigger than 0. So the case here that we need to have is that we are working only on here, positive numbers. Okay? There are many ways to prove this result. We can, in fact, we can get this function f of x, ln of 1 plus x minus x, with x is in this interval 0 plus infinity, and we can study this function and we get this result, this conclusion. Okay, but for us, we're going to use the mean value theorem. Okay, so for that, let's define this function. F of t is ln of 1 plus t on this interval 0x. X is positive. Okay, according to the mean value theorem, this function is defined continuous on 0x and also differentiable on 0x, not included the 0 and the x. Therefore, there is some c in this interval 0x such that f prime of c is f of x minus f of 0 over x minus 0, which is x. So f of x is just ln of 1 plus x, and f of 0 is just ln of 1, which is 0. So therefore, we have ln of 1 plus x over x. And the derivative here for this function is f prime of t is just 1 over 1 plus c. Therefore, if we plug t for c, we get 1 over 1 plus c. Okay? Now, we're going to bracket the c. So c is between 0 and x. Okay? So adding 1 to all the sides gives us this one. So if we flip this one, we get 1 over 1 plus c is between 1 over 1 plus x and 1. But this one is just this. Therefore, we have ln of 1 plus x over x is between 1 and 1 over 1 plus x. Since x is positive, we can multiply without changing something, nothing changing, sorry. So we get this result. And this is what we need. Okay, we have proved it. So most of the time, the mean value theorem gives us two results, but we need only this one on the right. So for x positive, the natural log of 1 plus x is less than x. Now we're going to use this fact here. Okay, since we are given that these ones, okay, the terms of the series or the sequence of the sequence are all positive, we can use this fact here. Okay, that means we have for all n, we have ln 1 plus a sub n is less than a sub n. Okay? This is the comparison test, the starting of the comparison test. Now we need one more condition. If this series defined by an is convergent, then this one is convergent. But we already have this one. We are given that this one is convergent. Okay? So taking the limit, okay? So the sum, okay, ln of 1 plus an from n going from 0 is less than or equal to this one here. But this one is convergent. Therefore, this one is convergent according to the comparison test. Therefore, we have it's finite. It's bounded above by something finite. That means it's convergent. So this is the conclusion. That means the natural log of 1 plus an is convergent. Okay, so this is according to the comparison test. Okay, so we have proved that the series defined by the natural log of 1 plus an is convergent. So we have used this fact here that we proved, okay, and also we have used the mean value theorem to get this one here, this result. We can also study this one here, this function, the natural log of 1 plus x minus x. We can use the derivatives. We can differentiate this one and see its behavior. And in fact, this one is always going to be negative. That means that it's decreasing. That means this is less than x. So that's what we need, but we are not going to do it here. So if you don't like the mean value theorem, you can just study this one, or you can just get it graphically. Okay, but graphically you get the idea, but it's not a proof. Okay, so by the end we have used the conditions of the comparison test. Okay, so we have used this one as some b sub n less than a sub n, okay, for all n, okay? And if this one is convergent, then this one is convergent. So we have this one, we get to this result based on this fact here. And we have this series as a convergent one, okay? Therefore, the comparison test let us conclude that this series, Bn, which is this one here, is convergent. And that's what we did. So these are the conditions for the comparison test, and this is the conclusion. Therefore, if we assume that an is bigger than 0 and the series an is convergent, we have the natural log of 1 plus an, the series defined by the natural log of 1 plus an, is also convergent. And I think this proves our result, and we end our video here.